I'm Pat Dugas. This screencast is about the graphs of quadratic functions, that is, functions that have a leading degree of 2. Now we're going to study the quadratic family of functions. The quadratic family of functions, and this is a group that has highest power of 2. In other words, the term in it that has the highest degree is a second degree term. They come in the form f of x equals a times x squared plus bx plus c. That first second degree term is called the quadratic term. The middle term, if it's in this form, the bx term, is the linear term. That's a first degree term. And finally, the 0th degree term is the constant term. Now, a, b, and c are real numbers. The a must exist for it to be quadratic. The b and c could actually be 0. Now, the quadratic family of functions has a shape of a parabola. Now, the parabolas can be stretched out, compressed, shifted, but they take basically one of two forms, either an upward-facing parabola or what we call a downward-facing parabola. And how you graph them is exactly like you graph anything else. You pick sets of ordered pairs and you plot them. So let's graph a quadratic function just by using a table. Let's take the graph of f of x equals x squared plus 3x minus 1, and we're going to make a table of values. So let's start by choosing integer values for x, and then we'll find out what the function gives us as output with those inputs. We'll graph the coordinate points, and we will create one of these parabola shapes that is indicative of. So the function is x squared plus 3x minus 1. We're going to take negative 3, put that as input to the function, see what we get as output. We take negative 3 and square it, plus 3 times negative 3 minus 1. Our result, negative 3 squared is equal to positive 9, minus 9 minus 1 gives us negative 1. So at the point x equals negative 3, we get y equals negative 1. Then we take the point negative 2. Negative 2 squared plus 3 times negative 2 minus 1 is negative 3. So the second point, negative 2, negative 3, is also on our parabola. Then we continue on, pick negative 1, we get an output of negative 3. Negative 1, negative 3 is on the parabola. At 0, always a good one to pick because it's easy to evaluate. 0, negative 1. And similarly, 1, 3 are all on this parabola. So if we take this set of 5 points, and 5 is a good number of points to be able to sketch your parabola, assuming you have picked good points to do so. If we graph these 5 points, then we get this parabolic shape here, all the way from negative 3, negative 1, negative 2, negative 3, negative 1, negative 3, 0, negative 1, and 1, 3. That's how we graph a parabola. 5 points, well chosen, should be enough to give you that shape. Let's look at kind of the key parts of a parabola in the form y equals ax squared plus bx plus c. So just as a linear function has a y-intercept, a vertical intercept, where the value of the input is 0, so too does a quadratic function. So if we put in a 0 into ax squared plus bx plus c, we always get the c term, that constant term, left over. You can quickly look at a quadratic function, just like you can a linear one, and see the y-intercept. So the y-intercept occurs at the point 0, c, where c is that constant term. Something that a quadratic function has that a linear function does not is called an axis of symmetry. Think of this as a line that divides that shape into two symmetric parts. You can see in a dashed red line the axis of symmetry for this particular generic parabola, this particular quadratic function. And something that's true of all axes of symmetries for these quadratic functions is that it occurs along the line x equals negative b over 2a, again where a and b are those coefficients of the quadratic and linear terms respectively. X equals negative b over 2a divides that parabola into two congruent parts. And so that is the equation of a vertical line passing through the x-axis. So that happens to be the x-coordinate of the vertex as well, and the vertex is either the minimum for an upward facing parabola or a maximum for a downward facing parabola, but the x-coordinate of that vertex is negative b over 2a. You plug that into the function to find the y-coordinate if you need it. Let's put this information to use. Suppose you're given the quadratic function f of x equals 2 minus 4x plus x squared. Find the y-intercept, the equation of the axis of symmetry, and the x-coordinate of the vertex. So first of all, this isn't in the form that we really like. So we're going to rearrange it from the leading power down. So we're going to go and rearrange these terms so that they fit our ax squared plus bx plus c model. We rearrange the terms such as the x squared term is in first, and then the linear term is second, and finally the constant term. That tells us that the a is 1. Now there isn't a number in front of the x squared, but from algebra we know if no number is given, it's assumed to be 1. So the coefficient of the quadratic term is 1. The coefficient of the linear term b is negative 4, and the coefficient of the constant term is 2. That's going to help us determine the y-intercept, because remember, the y-intercept can be determined directly from that c term. Therefore, the y-intercept is the point 0, 2. It's important to remember that the y-intercept is an ordered pair as a point. So now we're going to use a and b to be able to find the equation of the axis of symmetry. So x is equal to negative b over 2a gives us the equation of the axis of symmetry. We take the b and the a numbers and put them in. B is negative 4 and a is 1, and so we get negative 4 over 2 times 1 with a negative sign in front of it because it is negative b over 2a. The axis of symmetry occurs along the line x equals 2. Be super careful about negatives. This is the #1 mistake made in determining axis of symmetry and vertex. So the equation of the axis of symmetry is x equals 2, and therefore that is the point. The x-coordinate of the vertex is at 2. Now if we needed to find the y-coordinate, we would put it back into the function to find it. So now that we know that the axis of symmetry evenly divides the quadratic graph into 2 parts, use the axis of symmetry as kind of the center point in your graphing. So if we take this function 2 minus 4x plus x squared and wanted to make a table of values that includes the vertex, we know the vertex is at x equals 2. So we're going to use x equals 2 as our center point, and we'll pick numbers to the left on the number line from 2 and to the right on the number line from 2. And so keeping 2 as kind of the center point, we pick 0 and 1 and 3 and 4 on either side, the negative side of 2 and the positive side of 2 for our graph. And if we plug each of those numbers into the function, we get the point 0, 2, 1, negative 1, 2, negative 2, 3, negative 1, and 4, 2. And when we graph that, we first draw the axis of symmetry through the line x equals 2, and then we graph the 5 points. Remember I said 5 points is a really good number for graphing a quadratic because you have if you use the axis of symmetry as 1 point and then you pick 2 numbers to the left and 2 to the right, you're in good shape. So this is what the function looks like. Possibly the most important concept with quadratic functions in terms of their use is finding the minimum or maximum value of the quadratic. This is done by finding the coordinates of the vertex because the vertex is either the minimum of an upward facing parabola or it's the maximum of a downward facing parabola. Now it's also important to note that parabolas open up when their a term is positive. That kind of makes sense because that ax squared is by far the most important term in determining what's happening with that function. And so if a is positive, it's an upward facing parabola. If a is negative, then it is a downward facing parabola. So once we know where the vertex is, and we know whether it's an upward facing or downward facing parabola, we can determine whether that vertex is either a minimum or a maximum. In this screencast, we looked at the details of quadratic function graphs, especially their vertices, minimums, and maximums.